Hello. Today is March 26th, and we have been working on lesson 6-2. And so I wanted to show you a couple things. First thing is the explore and reason. And so we've got an initial number of bacteria and 4 different cultures. In each, that initial amount stays the same, but the growth rate per day does change. And so the time also changes. And so the first step is to fill in the table. If you haven't, you would want to fill this in by using an exponential growth function. That function would be 10,000 times 1.08 raised to the first power. That'd be for the culture A. As you go down, your equation is going to change because you're going to have 10,000 times 1.04 raised to the second power. The growth rate is changed to a decimal, added to 1, and that becomes your growth factor. What we see is that the relationship between the daily growth rate and the time is pretty much 0.08, because if we take 0.08 times 1, or if we take 0.04 times 2, or if we take 0.01, that 1% at the bottom, times 8, we have that 0.08. And so in part B, when we look at this at 16 days, our value is still increasing. So by compounding this, or by increasing that exponent, we find that even when we have the same initial value, we end up with a greater number of cells on the last day. So another situation that we could represent using an exponential function, you've worked a lot with bacteria in the past. You have worked with germs. You have maybe talked about telling a secret and how it spreads like wildfire. When something goes wild on YouTube, viral they call it, of course, COVID-19. And so we have a lot of situations in life that are exponential. Investing is another exponential situation, and so we're going to lead up to some exponential functions for investments. This one is a population, so this is example 1, and in this they're saying, okay, this T is the years, and so, well, to identify the monthly growth rate, we need the exponent to be in months. So we know that there are 12 months in every year, so 12 over 12 would be the same as 1 year. And what our example is showing us is that as we go down, we can use a power to a power rule to find the monthly growth rate. In this textbook, they are using 1/12 as an exponent. And if you're like, well, can't I just divide by 12? You can notice that we're going to be off. So we get 0.00205, whereas down here we're at 0.00208. And so we're off just ever so slightly, and your book really would prefer that you use this method rather than just dividing by 12. I picked out another example to show that subtle difference. So you're going to get really close, you're not going to be exact if you divide by your number of times. This is a huge idea no matter what textbook that you go to, but when we compound interest, we are looking at the formula that where P is the principal invested, R is the annual interest rate written as a decimal, N is the number of compounding periods, and so then N you can see in the exponent also. So N appears twice in this equation, once where we're dividing by the rate in order to figure out the monthly or daily or semi-annually rate, quarterly rate, and then we're again multiplying that so that we stay in that year. The value of the account after T years. And so as we continue on, we will be applying this concept to, like I said, annually, semi-annually, quarterly, and monthly. And as the number of compounding, can you see that down there? Oh, I turned it a weird color. As you see that down there, you can see that the number of compounding periods increases, the amount in the account also increases. So the more often we compound it, the greater the account becomes.